Okie dokie, so let's go ahead and get started. First things first, I have posted the next project. This counts for Robbie and not you, so you can do it if you want, though. What?
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 What are you saying?
He doesn't have to do the project. He's auditing the class.
Oh, you are? Oh, I didn't know that.
So
Trying to pull a fast one on me.
happy day, Robbie. You get to do the assignment.
Crushed it.
So this is project 2. This is two-dimensional heat conduction in a plate. Should be fairly self-explanatory. We should have done this a couple times in your education. Let me just go to the picture here. We have a plate. Okay, plate. It goes from 0 to L, 0 to W, constant thermal conductivity, specific heats. And the theta will get explained here in a bit. Anyway, we're going to take this plate and we're going to discretize it. And we're going to use finite difference to do that. So if this is node ij, then this is I plus 1, j, j plus 1, and j minus 1, I minus 1. Okay? Pretty simple. So for our finite difference, I should say the theta comes from the analytical solution. So we take this and we introduce a similarity solution. For those of you who took my fluids class, you should recognize this kind of idea. And this transforms equation 1 into equation 2, which just depends now on theta. All right, and we have some boundary conditions for theta, and we get an exact solution that looks like this. If you use separation of variables. So anyway, for this problem, we have 3 sides, 1, 2, and 3, which are all set to 0, and the top is going to be set to 1. Anyway, so we get that, and we get the following equation 6 here, which is our finite difference problem. So basically, in the end, if we assume delta x equals delta y, then a given node is really just the average of the nodes surrounding it. So that's pretty simple. So at this point, we now need to figure out how to solve it. So I'm going to actually have you do it 3 different ways. The first is with Jacobi iteration. So you have 2 different data arrays, an old array and a new array, and you take the old values and you plug them into the new values. So that's fairly simple. And you just keep doing that until it converges. Gauss-Seidel is slightly more complicated. This only uses one array because you take the values from that one array and then compute the new value and plug it in. So we're using new information. So if we solve this node here, then we take the 4 points surrounding it and we put that value there. Then when we go up, we take the 4 points, but now we're using that new value instead of the old value. Does that make sense? Okay. And then the last one is called successive over-relaxation. So with this one, you actually solve a node in a Gauss-Seidel fashion, but before you update the array, you modify the answer using equation 7. We have this omega term here, and that is a value between 0 and 2. Okay, this is called a relaxation constant. And notice that if omega equals 1, then this part goes to 0, and we're left just with the Gauss-Seidel version. Okay, if omega is equal to 0, well then nothing changes at all because we're just left with our old value. So that's a bad idea. And so if omega is less than 1 but greater than 0, we are relaxing the update, in which we are only using a percentage of the update. And this is good for nonlinear problems. What we have here is actually a linear one, but just FYI. But then the important part is if omega is greater than 1, we are over-relaxing the update. And so we're basically saying the update, if this is the old value, this is the new value, and it was going in the right direction, it's going towards the correct answer, and we're just going to keep going a little bit more in that direction. And so it can increase our convergence. So the actual assignment is to solve this problem using all 3 numerical methods. Use L equals W equals 1 with the number of nodes in each direction in X equals N, Y equals N. Okay. For each numerical method, I want you to measure 3 things for a given N. Is the number of iterations it took to converge, the total wall time it took to solve, and the wall time per iteration. For the SOR method, I want you to play around with omega. Try and find one that minimizes the number of iterations it takes to converge. In order to calculate convergence, do it using this equation here. And I want you to solve until that value becomes less than 10 to the minus 13. Okay? So what you're going to submit to me is a tar file with your code, a make file which has 3 targets. The all target, which will compile your code, clean, which cleans up any unnecessary files, and run. And so the run command in this case should run a single Jacobi case with n equals 100. Okay, so that should be fairly simple. I want you to provide a contour plot of the correct answer and 3 plots which compare the 3 measured values. So I want you to have 1 plot for number 1, 1 plot for number 2, and 1 plot for number 3. And so on the y-axis, you'll have, number of iterations to convergence. On the x-axis, you'll have n squared. That's the number of values we're updating. And so n squared should vary between a small number and a large number. And just see if maybe I actually don't know how this is going to turn out. So I want to see, if can we see cache problems with each method. That's kind of what I want to see if that shows up or not. And I don't know if it will. Anyway, so provide short paragraphs explaining your results along with some text on which method you would prefer to use and why. Okay, so it's kind of a big project, but this is an important project because it's going to set us up for doing this all over again in parallel. Okay, so we got to get this through this part first. Anyway, so any questions, email me, come to class, the 10 of you that aren't here. Ask me questions. So that's that. So this is actually the last part. Today we're going to go over the last part of serial optimization. After this, everything's going to be parallel from now on. Okay, so we're really getting to the fun stuff here. And so chapter 3 is on what's known as data access optimization. And so, yeah. All the little optimizations we talked about previous to this really aren't too technical in a way. But this is really kind of getting down into the nitty-gritty of things. And data access optimization is all based on how much stuff can we keep in the cache. Okay, how much can we keep in the cache and can we reuse that information? And so these are techniques to do that. However, we need to talk hardware for just a little bit more. And we're going to start by looking at figure 3.1. Okay, for those of you who aren't here, there's figure 3.1. Okay. So the idea here is that every piece of memory has 2 important terms associated with it. The first being latency, which is how long it takes to load memory in and out of that location. And and the bandwidth, how much information can be moved. And you'll see that there's a hierarchy here. We've got the L1 cache, which has a latency of nanoseconds, and then a bandwidth of 10 to the 11 bytes per second. So that's a lot of bytes. However, then we have the L2, L3 cache, which is slightly less, main memory, which is less, and so on until we get to the internet, which has a latency of 0.1 seconds and a bandwidth of 10 to the 7 bytes per second. So don't try and do things over the internet. It's really slow. Alrighty. And then I wanted to show figure 3.2. So figure 3.2, those of you who can't see it, there it is. Okay, figure 3.2 is showing the peak bandwidth, so memory bandwidth. Let me make this thing bigger here. And why is that thing always there? Okay, so here we have the time scale, and we have megaflops or megabytes. Okay, so basically what this is showing is that peak arithmetic performance. So this is kind of your megaflops. In 1994 and all the way up to 2010, okay, we had peak arithmetic performance was down here, and it kind of goes up, kind of goes up like this, and then it kind of jumps up a little bit more. Okay, so that's your megaflops, how many megaflops a given computer could do at that time. And then the peak bandwidth, which is how fast the memory can transfer information, looks something like this. All right, so this transition point here, this is when the world changed to multi-core processors. And that was in 2005, it looks like. So right before I graduated high school. Yes, I am that old. Anyway, the important point here is that now, especially now, the memory is what's going to slow us down. The memory makes a gap between the two. The current hardware memory controllers cannot feed information fast enough to our machines. And so the idea here is that if we can keep everything in the cache, we don't have to worry about that. Okay? And this is what they call machine balance. So a particular piece of hardware has what's called the machine balance, which is how much computation versus how much memory bandwidth is available in the machine. I'm at the wrong place here. And equation 3.1 yeah, so this is the machine balance, which they call BM equals the memory bandwidth. I spelled that wrong. Oh well. Over peak performance. Now the book goes a lot into very technical details that we're not going to go into, okay? But it is kind of fascinating. So if you want to read it, you can. But I just want to point this out, that the memory, the machine balance is the memory bandwidth over the peak performance, and it's very important. If you can get those to 1 or greater than 1, then you don't have to worry about that quite as much. However, it's usually not that great, honestly. So then the next important piece of information is what we call the code balance of a loop. Since we're doing numerical computing, we usually have lots and lots of loops. And so every loop is going to have a code balance, which is very similar to the machine balance, which is the number of memory operations over the number of flops. So for our vector triad, we had AI equals BI plus CI times DI. So here we have two floating point operations, 1 and 2, and we have 3 loads. So we're loading 3 values from memory. And then we are storing 1 value into memory. And so for this loop, the code balance is 2, because we have 2 flops, 3 loads, 1 store. So we have 3 plus 1 divided by 2 is 2. And another important thing to note is that store or write operations typically take longer than a read operation does. And there's technical reasons for that, but that's just important to know. The fewer stores you have, the better. All right, now that I've completely screwed up this slide, we can move on. Okay, so this isn't part of the book, but it needs to be talked about because everyone submitted Project 1 using C++, so we have to talk about C++. Typically in our numerical world, we like multi-dimensional arrays, and the reason being they are convenient for what we do. C and C++ do not have these types of things natively. Fortran does, MATLAB does, Julia does. Anyway, so the question is, how do we do this in C or C++? And so there's a couple options. If we did a double pointer, first off, whoa, that's yellow. Let's not do yellow. First off, it's really annoying because we have to write these big initialization loops. Well, first we have to do what? A equals new double star stinking thing. Give me a star. N. And then we have to do I equals 0, I less than N. And then we have to do A, I equals new double N. Okay. And then at the end, after we do everything, then we have to do an exactly opposite loop to correctly delete all that memory. Okay, so that's annoying, first off. And secondly, we run into this problem. So every time we allocate memory, so for that first allocation, we allocate a big array of pointers. Pointer, pointer, pointer. And each one of those points to a row of memory, like this. The problem is these rows are not contiguous in memory, meaning they're not lined up one next to each other. I mean, they could be, but we don't know that. And so we get a lot. What ends up happening is when we get to the end of a row, we will absolutely incur a cache miss because it has to go and find the next piece of memory. Okay. If we did in C++ a vector of vectors, we would have the exact same problem. All right. So then, what about this idea? What if we just had one pointer? that points to a giant chunk of memory. Okay, and this is what people tend to do in C, I've noticed, is that they have one giant chunk of memory, and then they define some macros that access it as if this chunk of memory were really a 2D array. Does that make sense? Okay. Problem with this is it uses macros. Macros are annoying. Plus, you can't. You need to know the dimensions of this 2D array in order to correctly resize what we have here. So there is that option. And compilers usually work pretty well with those because in the end, your indexing operations just look something like this. We have D1 times I plus J. Okay, and so this is what it would look like. That's how you correctly do a 2D array. Index a 2D array in C. And with only 2 dimensions, C++ compilers are usually pretty good at that. So there's that option. Then we come to the libraries. All right, so I have a library that I made for my research. I call it Fort C++. It's supposed to be an array class that acts like a Fortran array. So there's that. It was my array class was inspired by Eigen. Only problem is Eigen only goes up to 2D arrays. And I will say Eigen is the greatest thing I've ever seen. Okay, so definitely worth looking into. And I will say this, there are a billion other options. Okay, it's C and C++. Everyone wants to post their code on the internet. So there are lots of these. But if you're going to do anything, I would recommend, let me try that again. One of these 3 options. Okay. So that would be my recommendation. Anyway, so now we come to a very important point, which is storage order. And this part actually is in the book. This is very important when you're writing loops. So we come to the column major storage order or the row major storage order. Column major is the default for Fortran, MATLAB, Eigen, Julia, my own arrays. Okay.
Eigen, is that the Eigen class?
That's the Eigen class, yes, up here. Row major order is used in C and C++. It's used in Python's NumPy. It can be used in Eigen, and it can be used in my class. Okay, you can change that. However, Eigen doesn't recommend it for their stuff because they don't completely test row major order. And for mine, it works correctly either way. So, and I'm going to explain on the next slide. I have a blank slide that I can draw on. I came prepared. So, if we have, say we went with the double star route, or you could use a vector of doubles. Either way works. Okay, what that is going to give us is a big long chunk of memory in a big long line. And we have indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that was convenient. Now let's say what we really wanted was a 2D array, which is a 5x2 array. Okay, so we're going to call this our columns, and this is the number of rows. So what we get looks like this. Like that. So, a column major ordering is going to start here at the top left and go down the columns. So this would be index 1. This would be index 2, 3, 4, 5, 6, 7, 8, and 9. So that's column major. If we did this in row major order, it would look like this. Index 0 is here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay? And this is very important for when we're writing loops. So, let's say, since we're on row major, we have row major. We're going to say I equals 0, I less than 5. Is that right? And then we have another loop. And then j is less than 2. All right. So then we're going to access our array as follows. I comma j. And I did that wrong, actually. This should be 2 and this should be 5. So the idea here is that 0 and 1, and then 0, 1, 2, 3, 4. So the black here is the multidimensional index, while the blue is the linear index. Okay, so there's my linear indexes, and this is how we order them. So we need to access these in memory order, in the way they're laid out in memory. And so we do that by specifying the loops in this direction. So you'll notice if I is equal to 0 here, so that's column 0, and j is equal to 0, that's row 0.
Backwards.
Column 0.
No, I know, but
Row 0.
I would be the row in the. Yeah, I would be the row in this case. J.
So that's I.
Oh.
And that's
okay.
J.
Okay.
Got it?
Sorry. Yep.
Okay. And so we are accessing the 0th index. And then when j gets incremented, so j is now 1, we are looking at row 1, which jumps us to index 5. And I completely did that wrong. I screwed that up. Let me start this over. This stuff is confusing, okay? And it's necessary to understand it. And I thought I understood it good enough to just draw it out. Apparently I don't. Okay, let's start with the blue again. Okay, so I had this part right. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have our multi-dimensional index. Okay, so this is j, and this is I. Okay, so we have our loops, and I'm just going to write some shorthand here. I equals 0 to, well, 2, less than 2. And then j is equal to 0, which goes to less than 5. And then we're going to access it like this. Okay? So so this is how this works. At the very first iteration of both loops here, we're going to access that one. And then on the next iteration, j is equal to 1. So we go j equals 1 and we move here. Now, because of the cache line thing, when we pull this value into the cache, it's going to pull the entire cache line, which is probably going to be, something like that. And so 1 is already in the cache. And then we move on, 2 is already in the cache, 3 is already in the cache, until we get to 4. At which point it pulls the next cache line, which is going to be these values here. And so it moves on. So now we've reached the end of our inner j loop. So this is the inner loop, and we've reached the end of that. So now it jumps up to I equals 1 and j equals 0, which pulls number 5, which just happens to already be in the cache. Okay? And so that's the correct ordering. If, however, the loops were switched, we would have a different problem. I wish I could just erase black. Is that possible? No. Okay, so let's use a different color, huh? Let's use red. So now if we switch these loops, okay, the very first iteration is going to pull that guy there. Okay, the very first one, 0, 0. That's simple enough. But then the next loop is going to be I equal to 1 and j equal to 0, which pulls that guy, which he's not part of this cache line. And so we get a cache miss, and it has to go fetch this from memory. And we're iterating through that in the wrong order. Like that. Does that make sense? So you have to make sure your loops are in the correct order, otherwise you're going to have a ton of cache misses because you keep skipping lines. So, again, you have to know what storage order you're using. And there's a simple way to make sure you keep your loops in the correct order. Okay? Here's how you do it. Especially because it's hard to think about this once you move past 2 dimensions. Once you get to 3 or 4 or 5 or 6 or 7, it can become a pain in the butt. So, if you are column major, then when you're writing your loops, say you had a rank 4 array here, the column major always increments that one the fastest. Okay, so that's I, which means we're going this way. So it always increments the first index the fastest, that one's next, and that one comes up last. And if you are row major, then it's the opposite direction. This index, the last index, gets incremented the fastest. And so that should be your inside loop. And that should be your next loop, and that should be your outermost loop. Does that make sense? Quizzical looks.
That picture. Oh.
Sorry.
It's okay.
What were you going to say?
Well, that picture that you drew on there, can you go back to that or no?
No.
Okay. It had the arrows drawn down, right? But that wasn't the shortest.
You talking about the column major one that I had?
Yeah, so you had
Okay.
0, 1, 2, 3, 4, 5, and then 6, 7, or 0, 1, 2, 3, 4, yeah. Right.
Okay, so we have 2 different styles
Correct.
to do this, okay? Column major and row major. So the column major is going to take your big long chunk of memory and access it in a column fashion.
Right. So that one would be the arrows. So it would access the columns the fastest. So the cache would be those first two columns.
Right. It would pull in those 4 values.
Whereas in the row, the cache would be the first 4
Right.
columns on the top row.
Exactly.
Okay.
It's called row major because you run along a row.
I think that might have been switched in your. I think you might have drawn that backwards. That's why I was confused.
Okay.
Maybe I'm mistaken, but I think.
Well, you can go back and watch the video and tell me. But the basic idea, yes, is that you run down the columns. In a column major, you run along the rows in a row major. And so the important thing to remember is that if you're column major, you want your loops to start, your innermost loop should be the first index, all the way out to your outermost loop, which should be the last one. Whereas if you're row major, you should start at the outside. So the innermost loop should be the last index, and your outermost loop should be the first index in row major. So that's the big takeaway there. Otherwise, you're going to incur lots and lots of cache misses. All right. So now, what time is it? Yeah, go ahead. Oh man, time goes fast. Okay. All right, so algorithm classification. I'm just going to skim over this. These are how you get highly optimized linear algebra libraries. Every algorithm can be classified by the number of, and I think it's actually switched in this, which is confusing, but this is the flops versus the number of bytes or memory operations. Okay, so n is, say how many points you have in your grid. So if both the data transfer and the computations are proportional to n, we have an ON operation. These are, say, scalar products, such as A equals S times B. Vector additions, C equals A plus B. Sparse matrix vector multiplication. And we can use a technique called loop fusion to get a slight speed up, constant factor of improvement. All right, so then when we have an ON squared, this is a typical 2-level loop. There are n squared operations, n squared loads and stores. This is like a dense matrix vector multiplication, matrix transpose, matrix addition. We can use techniques such as loop unrolling and loop blocking to achieve better speed up. But if we have an ON3 versus ON squared, where the number of operations grows faster than the number of loads and stores. Basically what that means is as n gets bigger, we can reuse our data a lot because we're doing lots of operations with it and we don't have to keep moving it in and out of the CPU. And so this is like your dense matrix multiplication or dense matrix diagonalization. So I'm going to talk about each one of these. So loop fusion achieves a constant factor of improvement. It can increase register pressure, which can cause register values to spill over, which will actually slow down your computation. And compilers could possibly do this optimization on their own for simple loops. But the idea here is if we have 2 loops that are computing 2 different things, so we have AI equals BI plus CI, and we have a second loop here that does ZI equals BI plus EI. Okay? The idea here is that we can combine the 2 loops together, and what we get to do is reuse the B array. So we've eliminated a single load. We don't have to load B a second time. So we've saved time by reusing B. And so that's the loop fusion optimization. It's fairly simple. Any questions on that? All right, so loop unrolling. This one is more useful. It's also known as unroll and jam. It does increase your register pressure, but it reuses data in a single loop. Compilers tend to do this one a lot if they can help it. But the basic idea here is if we have this double loop here, so we have a double loop, and this is actually a matrix vector product. Okay, so we have a matrix A and a vector B, and we're storing that into vector C. Okay, so we have something that looks like this. Everyone see that? And I missed a line. There should be another line in here. That needs to be in here. Anyway, so the idea here is we're going to take this outer loop and we're going to have it skip by 2. Okay, so, and then on the inside of the inner loop, we actually are going to execute 2 operations at the same time. So we're going to do CI and CI plus 1 at the same time. And you'll notice here, since this is Fortran, we're actually not, we're doing 2 completely separate rows at once. But what it does is we get to reuse B, and assuming that our computer has enough hardware space or enough cache space, we're basically running 2 different cache lines at the same time in matrix A, and we're storing these into CI and I plus 1, which are right next to each other in memory. Does that make sense?
I think so.
You think so? It's okay. We're not going to be focusing on this, but it's important to know what these things could be using. And then the last big one that everybody rants and raves about because it's so awesome is what's known as loop blocking or loop tiling. What you do is you block the loops. So we take this here and we put more loops on the outside. We do 1 loop for I, 1 loop for J. And we define a chunk of I. So here's a chunk of I, and here's a chunk of J. And I did not write this correctly, because this should be I start to I end, and this is J start to J end. So we define this big, basically if this is our matrix A here, we're going to take this block. So these 2 outer loops separate out that chunk, and then we loop inside of this 1 chunk. And so the important point is that that chunk fits into cache. It's small enough that it fits, and we operate on it. And then we spit it out. And we do the next chunk, and we operate on that. And we spit it out of the cache. And we do the next chunk, and we operate on it and spit it out of the cache. And so we're done with that entire chunk. And so we don't have to Usually, I mean, in this method, what we do is we just run through A. La, 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 la. But that incurs lots of cache misses, and it's called a streaming operation. So we've taken our streaming operation and we turned it into a block operation. And the teeny tiny block operations fit inside of the cache, whereas the streaming operation does not. And so when you combine loop blocking with loop unrolling and some other optimizations that we're not going to talk about, you get super fast code. So guess what? You don't have to do this. Okay, we're not focusing on this. We're going to focus on the parallel portions because people have made optimized libraries already. And believe me, it's a pain in the butt to do correctly. All right, so the first big thing I want to talk about is BLAS and LAPACK. This is a standard which is implemented by several groups. It's also the de facto standard for pretty much all linear algebra. Okay, BLAS defines simple matrix operations, while LAPACK defines linear algebra operations. There is several different implementations of this. OpenLAPACK, that's what you get by default on Linux. Atlas BLAS is actually really cool. It's a program that tests your machine and figures out, well, I should say, I'll go back. You'll notice here we have a B there. That's the block size. And in loop unrolling, we have this 2 here. That's your loop unrolling size. And that is dependent on what machine you're running on. Okay? Both of those are. For the optimal thing. And Atlas BLAS, what it does is it actually runs for a long time and tries various combinations of everything until it finds the optimal combination. Then we have the Intel, I think it's like matrix kernel library or math kernel library or something like that. No surprise, it's actually generally the fastest version of LAPACK you can find. Then there's, of course, ScaleLAPACK, which is a parallel version of everything. And again, there's another one called PETC or something like that. Anyway, that's a parallel matrix thingy. Anyway, so there's lots of implementations, but this is generally what you're going to find. Since we're all working in C++, I want to highly recommend Eigen. Eigen is a C++ library. It's written entirely in C++. There's no Fortran or anything. It's used by Google, so it's got to be good. It's free. It's easy to use. Their documentation is fantastic. So I would definitely recommend this if you're using C++. And they claim that they achieve performance that is better than most open source versions of LAPACK, and they claim they get close to the Intel MKL. And so they use lots of advanced meta template techniques to achieve that kind of performance. It is dependent on your compiler's ability to inline stuff. And it's what I used to learn how to write my Fort C++ array class. So, my takeaway for this lecture is try to write your numerical methods in terms of matrix math, because then you can use an optimized library and you'll know it's going to go fast. This is really, really important if you're using a scripting language like MATLAB or Python, because loops in these languages are really slow. So if you can put it in terms of the matrix math and use the built-in matrix operations, it's going to go fast. If you have very large matrices that are sparse, meaning they're mostly 0 everywhere, then you should find a sparse matrix linear algebra library. I've never used them, so I'm not an expert, but Eigen has one. So there's that. Also, make your matrices as large as possible. because the libraries are generally optimized for big matrices. If you have small ones, it might be faster to write your own. Well, it wouldn't be faster, but it would run faster. And you'd have to make sure it actually works. But you should always test it. And so the optimizations discussed in this lecture, they are generally a last resort. Okay? Because they make your code difficult to read. They're time-consuming, error-prone, and difficult to maintain. Okay? So rely on someone else who is more of a nerd than you are to to do that. Okay? So that's my lecture for today. So anyway, tomorrow we get to start on the fun stuff. Okay? Project is due next Wednesday. We're speeding up a little bit because what?
The second project.
Yeah, the second project is due next Wednesday. The first project is due this Saturday. We're going to start going into parallel stuff, and that's going to be lots of fun. So anyway, that's all I have today.
It's fun.